Okay, guys, good morning, good afternoon, good evening, good night. Good night to all of you from all around the world. So, welcome back to our My PCS Malaysia Process Control Society webinar series, which is we have this one for number 6 for this year 2021. So, today we are very fortunate to have one of the world known process control professor. It is Professor Sigurd Skogestad from Norwegian University of Science and Technology, directly from Norway. In this webinar series, Professor Skogestad will present and discuss the topic distillation modeling and control. So before I give this session to Professor Skogestad, I just give a little bit information, the biography of Professor Skogestad. So Sigurd Skogestad, the Professor of Chemical Engineering at NTNU in Trondheim, which focus on process control. So he received a PhD from California Institute of Technology, Caltech. I'm reading your CV here from your website. Has been a full professor at NTNU since 1987. He was a head of department of chemical engineering from 1999 until 2009, which is 10 years. Then after that, since 2015, he's the director of the SAPRO, which is a Center for Research-Based Innovation on Subsea Production and Processing. So his research interests include process structure design, control structure design, and plant-wide control, optimal operation of process systems, modeling for control, robust control, PID control, and also distillation column. So without further ado, I would like to invite our invited presenter for today's webinar, Professor Sigurd Skogestad. The floor is yours, Prof.
Thank you very much for a very nice introduction. I think you covered most of my background, and I'm very happy to present this topic of distillation for you, because this is distillation. I've worked on for many years, since the beginning of my career, and it's one of my really favorite topics. In addition to process control, distillation has been my main interest. It's a very interesting process, and it's very important in chemical engineering. So I will try to give you some background about it here today. I hope you will enjoy the presentation, and as you were told, you can ask questions if you have as we go along. So you mentioned my CV already, so I will not go through that, but just point out that I have some red words here. That's the distillation. So I worked on distillation for many years during my PhD. I worked also when I was engineer before I started my PhD, working on mostly on simulations and design at that time. And then also after I became professor, many of my PhD students have been working on distillation. It's an important process, and it's very interesting also from a process control point of view. So just a little about where I'm from. You mentioned I'm from Trondheim. Trondheim is a small city in Norway, in the middle of Norway. You see here. Norway is in northern Europe, close to the Arctic Circle. You have a question?
No, continue.
Okay, yeah, it's close to the Arctic Circle. So the Arctic Circle is the border where north of this Arctic Circle you have midnight sun, 24 hours of daylight in the summer, and then 24 hours of night in the winter. So we are just south of the Arctic Circle. Otherwise, Norway is known for the fjords. This is the famous Geiranger Fjord, lots of fjords all the way along the coast here. Here's England and here's Germany. So that's Norway. So quite far from Malaysia, but it's, if you happen to come here, then please come and visit us. So then about the talk today, so it's about distillation, modeling, control. I'll start with an introduction, a bit about the basis for the process. Then I'll talk about a bit about modeling. Modeling is fairly easy in principle for distillation. I'll talk about a bit about dynamics, optimal operation, and then on control. So that's the topics. So let's start with the basis for distillation. So the basis for distillation is that you have a difference in boiling points or volatility. So you can see here, this to show you have a liquid phase here with several components, and you have a vapor phase in equilibrium. And then if you have vapor-liquid equilibrium, you will have that the light component will have a higher mole fraction in the gas phase than it has in the liquid phase. So Y is the mole fraction in the gas phase, X in the liquid phase. And a very important quantity is what we call relative volatility. So you take the ratio between the Y and X for the light component, which is going to be greater than 1, divided by the ratio between Y and X for the heavy key component, which is going to be less than 1. And you get a number that's alpha, which is greater than 1. So if it's very close to 1, it's very difficult to separate using distillation. If it's large, it's good for distillation. So this is an expression to estimate the relative volatility as a function of the boiling point difference. So you can see if there's a large boiling point difference, you get the larger alpha. Here's an example for isopentane and pentane, which is a fairly difficult separation. It has a boiling point difference of 8.2 degrees Celsius or Kelvin, giving a relative volatility of, according to this formula here, of 1.32. So that's a fairly difficult separation. Now, how do we use this in practice? Well, distillation has been around for many years, since probably 3,000 years at least. This shows you some typical apparatus that I used maybe 500 years ago, mostly, I guess, for maybe making alcohol or also making things like perfumes. So you put the liquid in here, and you put heat under here, and it starts boiling, and the vapor comes up here, and you cool it sending it through some water or something through the pipe, and the liquid product comes out here. Here's another design. Here's another one. Heat here, the vapor goes up over here, and it's cooled in this drum where you fill it with cold water, and it's condensed. So that's batch distillation, and it says no reflux. Now, I actually have in my office a couple of columns here, which is also batch distillation, but have reflux. I don't think you can see them here. I think so. So here, there's 2 columns here, a bit similar design. Both of them will have reflux. So you heat the liquid in the bottom, and the vapor goes up the column. And here's a condenser, so it will cool the liquid and make it into the vapor, make it into liquid. And some of the liquid is sent down the column as reflux, and some of it is taken out as a product. So the reflux is important because with the reflux you can get multi-stages separation also. So it's very important to have reflux. And reflux also makes it like a recycled process, so it makes it a bit more difficult to model and understand. So this is want to show you a continuous distillation column with reflux. This is how we separate in industry, and this is what is going to be talking about today. We have a column either with stages or filled with some packing material. And we have the reboiler in the bottom here, what we saw before. So this is where the heat is added, and vapor goes up the column. It meets the liquid. The liquid is coming in through the feed here. And it continues up to the top where it's condensed, and some of it is sent back as reflux, and that's very important, and some of it is taken out as a light product. So XD, that's the mole fraction of the light product. And then the heavy component goes into the bottom. to the B. XB is the mole fraction in the bottom. And you see here that you have many stages. Stage 1 is usually the reboiler, and you have stage 2 and all the way to the top end stages here in this case. So you can make a lot of stages by having a tall column, but you need to have a reflux to make use of these stages, of course. So when do you use distillation? Well, you use distillation for liquid mixtures with difference in boiling points. That's the main starting point. And it's a very effective and easy, good separation, used a lot of industry, probably the most used separation method. It's essentially unbeatable for high purity separation, and one reason is that the energy consumption is essentially independent of purity. It doesn't matter if you have it more pure, it doesn't cost more energy. And also the number of stages that you need to separate, that of course increases with the purity, but only in a logarithmic fashion. So it doesn't increase so sharply. Also, distillation columns are well suited for scale-up. You can have columns with diameters up to 15 meters. And it's used even for some unlikely separations, like all the silicon that's made for the computers is made by distillation via silicium chloride. Also, actually, heavy water separation is done by distillation, and it only has a boiling point difference of 1.4 Celsius. So it's used for many, many things. And one thing that you should note is, of course, that for close boiling mixtures with alpha close to 1, relative volatility close to 1, then you will generally need a lot of energy or heat, and you will need many stages. So there's this myth, I would say, that distillation is an inefficient process because it uses so much energy. Well, yes, it's true that it uses a lot of energy for difficult separations, but actually by itself it's an efficient process. Typically the thermodynamic efficiency of distillation is better than 50% in terms of the thermodynamic efficiency. So the reason people say it's not efficient is not because of the efficiency of the process itself, but it's because the heat integration may be inefficient. Because yes, it may need a lot of energy to do the separation, but it provides the same energy back again as cooling at a somewhat lower temperature. For close boiling mixtures, this temperature difference is very small. So actually, by having proper heat integration, for example, you could have a heat pump from between the top and the bottom. You can make very good heat integration and also get very good efficiency. So here I'm showing a plot of the efficiency of distillation, typically for a binary separation as a function of the feed composition set and for different relative volatilities. See, when relativity is close to 1, it's most efficient when you have 50-50, and you have relative peak efficiency is about 70%. So the thermodynamic efficiency is, you can say, the ideal separation work divided by this Carnot efficiency you're getting from the integration at the top of the bottom. And this is the expression for the entropy of mixing, and this is the Carnot efficiency. And if you use this formula, and combine it with this vapor, this boiling point difference formula I had before, you get this plot. So distillation is actually an efficient process. It's the separation itself is efficient in the distillation column. It's the heat integration that might be inefficient. And then about a second thing now to modeling. So modeling of distillation, it's in principle simple, and it's one of the simpler processes to model. It's a complicated process, but the modeling is simple. So normally what we use is the equilibrium stage concept. So we model the distillation as just many stages in series. each having equilibrium between vapor and liquid on the stage. You have the vapor coming in from the stage below, from the liquid above, mixed on the stage, assuming equilibrium, and then you have the model. So you can then from this, around this stage, make a component material balance for light and heavy component. You can make an overall balance for the liquid and vapor flows. You can make an energy balance. You have expression for the liquid flow, for example. You have the Francis Ware formula for how much liquid that flows out of the stage. So you have more liquid on the stage, more will flow out. And you have the most important in the end there is actually the vapor-liquid equilibrium relationships, the thermodynamic relationships. Like this is a relative volatility model. And usually this is the most important or most difficult step, that's to get this data or get this model. So it can be based on activity coefficients for non-ideal mixtures or for more ideal mixtures using equation of state. So when I was working in the company as an early engineer, a young engineer, 40 years ago, most of my work was into this part here of getting the vapor-liquid equilibrium. And then we're modeling various separations, like by doing crude oil distillation. I was doing vinyl chloride distillation and so on. But this was the key step, was to get this data correct. And you have a lot of software now today. You have HiSys, you have Aspen Plus and all these things, and you can quite easily model it. Sometimes people use non-equilibrium models, but I think in most cases the simple equilibrium models are efficient and are used in practice. So just a bit more details about how you do the modeling. Well, there's several parameters I need to adjust here. So that's of course, something the engineer needs to do. The first thing, as I mentioned already, that's the vapor-liquid equilibrium. You may need experimental data if you have a new mixture. Usually you have the data already in the software, but some cases you may need experimental data. Then you need to adjust the number of stages. Normally you do this by using a steady state model and matching it to real steady state composition and temperature profiles from the real column. So you adjust the number of stages to get a match between the temperature profiles and also composition that you're seeing. And you can also use the theoretical stages for packed columns, even though it's maybe not a good real relationship, or it's not really how it happens. It still is a very good way of modeling packed columns. For a tray column, where you have physical stages, then you may introduce things like Murphy efficiency. I often use, instead of this, use bypass. So I let some of the vapor bypass the stage, and I use this to represent non-ideal trays not having equilibrium or having bypass of the liquid. Instead of the Murphy efficiency, I usually use bypass. Then you need to have data for the holdup if you want to do a dynamic model. So then you can use data for how long the liquid takes from the top to the bottom, for example. Typically, you can also use typical data. Typically for a tray column, 10% of the volume is liquid, and for a pack column, maybe about 5% or less. And then you need to have data for how fast the liquid goes from the top to the bottom, and you can get this from measurements, because this liquid tray dynamics are very important for control. I'll talk about that later, but this is really important for control. The fact that it takes some time from the liquid to go to the bottom, so that needs also to be included in the model. So in summary, modeling is in principle fairly simple for distillation. If someone has any questions, I can talk about that later. But usually, if you get the thermodynamics right, usually a model of distillation is more to be trusted than actually the data from a real column. The modeling is usually fairly good in terms of matching the reality, from my experience. So that's about modeling so far. Then I want to talk a little about dynamics. So dynamics distillation are known to be quite slow or almost integrating slow responses. I'll show you an example here from a propane column, C3 splitter. It has a very low relative volatility of 1.12, especially at high pressure that we operate at. And it needs many stages, 110 vertical stages, maybe it could be 200 real stages, close to that. And you have high purity in the top for the propylene and a bit lower in the bottom for the propane. And it has a large reflux because of the difficult separation. So the reflux divided by distillate is close to 20 here. So let's look at how this column responds dynamically. So let's first make a change in what I call external flows. Okay, so what is external flows? Well, external flows is, so I increase the reflux, in this case only by 0.4%. So I make a small increase in reflux here, but at the same time I keep the boil-up constant. So that means that when I increase the reflux, I will need to decrease the distillate, and I will need to increase the bottoms. So there's less coming out in the top and more going out in the bottom. And that's why I call an external flow change, because the external flows to the column are changing. The feed is fixed here. This is fixed, and I'm essentially sending more of the product to the bottom. This will make it more pure in the top. Here you see the response in the top going from 99.5 to 9975 here. This is the response in the feed, and this is the response in the bottom. Look at the time scale. It's 2,000 minutes, so this is many hours. This is 30 hours or something. This is a very long time. So it's a very slow response here, you're seeing. If you look more detailed in the bottom, they will see that takes about 6 minutes from the liquid to go from the top to reach the bottom. From the top to this is a large column. It takes 6 minutes before this liquid change is felt in the bottom. So that's important actually later for control. That was the response for a increase in reflux. So let's look at the same thing. Let's increase this one instead, the heat input instead, while keeping the reflux constant. You will see that this is the same, just the opposite. Actually, no, before I show this is just showing you all the stages inside the column. All the 110 stages, you see they're all responding with a similar slow response with the time constant of several hours. So this was the increase in boil-up. You see goes in the opposite direction from before, and it's a quite large effect on compositions. You see, especially in the bottom, there's a large change in the bottom here. It gets much purer in the bottom in this case because I'm increasing the boil-up, and it's getting less pure in the top. So it's essentially the opposite of an increase in the reflux. So you can imagine what happens if I increase both of them at the same time by the same amount. So keeping then the distillate flow and the bottom flow constant. So that I call increased internal flows. So let's see what happens if we increase both L and V at the same time with D and B constant. And as you may expect, in this case, there's almost no effect. There's very, very small effect. There's an effect, and you're getting both products are getting slightly purer, but it's much smaller than what you had before. So this is a very important thing for distillation, that you have this difference between external flow changes and internal flow changes. So here I'm showing you a typical. This could be a temperature profile, but actually it's a composition profile. So I have the temperature or composition on this axis, and we have the stages here. So the blue line is the original profile, and then I made some changes in external flows, and over here I made changes in internal flows. These are actually 10 times bigger. So in reality, this is a very small change happening here. So what you see is a very big difference, that if you change the external flows, that has a large effect on composition, and one product gets pure and one less pure. If you make a change in internal flows, it's a much smaller effect on composition, and both products get either pure or both less pure. So this is actually, from a control point of view, this does not look good, because it means that it's very ill-conditioned or interactive, this process. And you would think that this gives you a problem for control. And actually, in my PhD thesis, I studied a bit this system, and I found out it was very difficult to control. I studied the system without looking at the liquid flow dynamics, because there is one very good thing for distillation. I mentioned this liquid flow dynamics. They're very important because they actually make control easier. So the liquid flow dynamics is the fact that when I change the liquid in the top, it takes some time to reach the bottom. And this makes control much simpler than it would otherwise be. Fortunately, all real columns have liquid flow dynamics, packed columns or tray columns, so that makes control easier. So here's again showing you the liquid flow dynamics. This line here is the increase in the top of the column in the reflux in the top. And I'm looking at the response in the bottom, the liquid that comes down here. And you see in this case, there's about 2.5 minutes delay before the liquid comes to the bottom. So the liquid flow dynamics, actually, they break the initial two-way interaction between top and bottom. And it makes it less interactive initially. So the implication for control is that you would like to close one loop, either using a temperature or composition, with a closed loop time constant faster than these liquid flow dynamics. If you do that, you will make the whole control problem much easier. That's an important insight, and especially this is important for systems that are difficult to separate, for difficult separations. So that's a very important insight for control later. Did we get any questions or anything so far here? Anyone has any questions? Please go ahead.
Hello, Doctor. So I have a question about the distillation column design. So for the design, are there like heuristic methods, or do we use model-based design?
Usually we use model-based design. Of course, there are what we call shortcut methods that are used, but normally we use the detailed models to do the design of the column, and it's in principle easy to model. The solution can be a bit difficult. It's not that easy to solve these equations, but the software today is quite reliable in most cases. So distillation is a process that's it's a complex process, but usually the models for the process are quite working well. So that's one good thing about distillation, that you have good models usually. Another thing I'll mention now is nonlinearity. So distillations are known to be very nonlinear. That's also a problem for control, of course, nonlinearity. Now, what you can do, and it's very common, is to use what we call logarithmic compositions. So instead of using the mole fraction, say, of the light component and controlling that directly, you take the ratio between the light component and heavy component mole fraction, say in the top product, and then you take the log of that, and you control this instead. So this is not only that the log makes everything linear, it also has a strong theoretical basis. Yeah, you have some paper where I've written about the why you can do this. You can also do it for temperature. If you're using temperature control, you can use something like this to get a more linear response. So this can be helpful for control. And this plot is just showing you how effective this is. So here I have a case where I made a step change in the reflux. So the first, and then I look at the composition in the top. So it's getting more pure. So the linear response is for a very small change in reflux. And this is shown the response over 30 minutes. Now, as I increase the change of the reflux, you see it's very nonlinear. Even after a couple of minutes, it's getting very nonlinear, and this is bad for control. But if I take the log that I just showed you, then it's much more linear. It's very, and the interesting thing is it's even dynamically, that's where it helps the most. And if you know about control, then you know that the dynamics is the most important for control, the initial response. So it makes it much easier to control if you take this transformation. So that can be a good idea to do in some cases. So just to make some conclusions so far in terms of dynamics. So what you see is that the dominant response is first order, and it's often close to integrating from a control point of view because the time constant is so large. The time constant could be several hours, and you don't want to wait several hours for control. So it's like an integrating process almost for control. Another important thing for control is that we have the liquid flow dynamics that decouple the top and the bottom on a short time scale and makes control easier. And the third thing for control is that logarithmic transformations linearize response, especially dynamically. So that's so far on the dynamics. So then I want to talk about the main topic here today, which is on operation and control. So the reason for building a distillation column is, of course, to separate the mixture and to overall to make a profit for the operator. So if you look at it from a control point of view, this is a distillation column. We have the feed here, the distillate product, the bottoms product. Essentially, from a control point of view, there are 5 degrees of freedom, 5 valves that you can change. They're shown by red here. So I've assumed here that the feed is given. And of course, there may be cases where this is used as a degree of freedom, but let's now, just for now, assume this is given. Then you have 5 degrees of freedom as the heat input. That's number 1. It's the reflux. Number 2. There's the cooling, which is used to control the pressure normally. Number 3, called VT here. And then there's the distillate flow, the product in the top, and the bottom flow in the bottom. So there's 5 degrees of freedom from dynamic point of view, but for a steady state that's operation, there's only 2 degrees of freedom normally because we need to control pressure and we need to control the 2 levels. And the 2 levels have no steady state effect, and the pressure also has a very small steady state effect and it's usually fixed. So there's only 2 degrees of freedom left for operation. So how do we adjust these 2 degrees of freedom to make a good operation? That's the question. And what we want to do is generally to minimize a certain cost. We want to define a cost function for the column, and we want to minimize this with respect to the 2 degrees of freedom, subject to satisfying constraints. This is the general problem for operation always. So if you look at the distillation now in particular, the cost function is quite easy to define. You can define a profit function for the column itself. So you can define that as the income, that's the value of the 2 products, is the price of the product in the top and the price in the bottom, minus the cost of the feed, minus the cost of the energy. And the energy includes both the heating and possibly the cooling cost. So that's, you want to maximize the profit or minimize minus the profit. And the constraints are on the purity. On the top, you have a purity specification usually. You have a purity specification in the bottom, and you have lots of capacity constraints like maximum flow rate you can have, maximum vapor, maximum pressure drop, and so on. So the question is then what's going to be optimal? So what will happen is it's sometimes you can have both these constraints being active. Then you want to control both the purities, but that's not so common. The case usually only one of them is actually active of these purity constraints, or not, or at least often only one is active, and the other constraint other end might be over purified. And that's because the reason for over purification is because you want to maximize the amount of valuable products. So it might be cases where you over purify to get more valuable product. So to say this more clearly, what are the expected active constraints for distillation? And the reason I put emphasis on active constraints is because these are things that you need to control. So that's important for control. So for the valuable product, the purity specification is always active. That's very important. This is to avoid product giveaway. So in this case here, I'm separating methanol and water and taking the valuable product methanol in the top. It has a maximum of 0.5% water to be sellable. And at the bottom, I'm taking out the water, which has a maximum of 2% methanol. This spec is because I'm going to send this water to some water treatment, and it cannot have too much methanol to be not kill the bacteria or something. So this is the specification, but this one will always be active. There's no reason to have more pure here in the top, because this will just cost you more energy and it will give you less product. But for the other product, so this is always active, the top specification. You only want to control this composition at 0.5%. But in the bottom end, it's likely that you will over purify, because if you send 2% methanol here, obviously you're losing product. You could send it here instead to the top. So it's very likely that you would like to over purify in the bottom. And this will not necessarily cost so much energy. If you have a lot of stages, it will not cost so much energy. If you have relatively few stages, then yes, it will cost energy to increase the purity. And it actually may be cases where you want to operate the column at the maximum heat inputs or maximum vapor flow here in order to maximize the amount of valuable product in the top. So what you see for distillation is the operation of the column will depend on prices, it will depend on specifications, and it can change all the time. So it's usually not the case that the distillation column will have the same control structure for forever. Things might easily change with time. Sometimes energy is expensive. You don't have vapor or heat available. Other cases, you might have a lot of excess energy and you want to use it here. So the control of the distillation column depends on what's around the system. But you need to be able to make a control system that adjusts to the market and changes. So we are over to control. So distillation control. So it has been studied in many papers, especially when I was a young engineer. There was lots of papers coming out, and it was very confusing. And it was difficult to understand what was going on. So I worked on this topic for many years, trying to make it more clear. The reason why it's a lot of different papers, because some people put emphasis on pressure control, other on level control, other put it on composition, and also the fact that many people don't really study distillation, they're more studying control theory. So then it's not really a distillation paper. I wrote a paper more than 10 years ago where I tried to sum up some of my experience, called the do's and don'ts of distillation column control. So some of the things I'm presenting here today are from this paper. So you can have a look at that if you want. Now, for control in general, there's two objectives. This is for any control problem. There's the first objective of stabilizing operation, avoiding drift, and the second objective of optimizing operation to make it profitable. So the second part has to do with this minimizing this cost and satisfying constraints. Now, for distillation, this means that you want to control the two levels and the pressure, because if you don't control the levels and pressure, it will not be stable and will be drifting. In addition, you usually want to control the temperature profile, in the level of heavy component, you could call it. And this is also because this is almost like a drifting thing. You remember it was like integrating, I said. So to stop this drifting, you often want to control a temperature inside the column. And then to optimize operations, normally we control product compositions. So those are the two things we want to control. remember that we have 5 dynamic degrees of freedom, and I controlled 3 things here, 2 levels and a pressure, and the temperature, 4 things here actually, and 2 things here. How is that possible? I have 4 plus 2, that's 6. Okay, why it is possible is because this temperature set point can be used as a degree of freedom for the steady state operation. So that's why 5 degrees of freedom actually is enough by using a cascade control system. So this is showing you typically how things are done in practice with the so-called LB configuration and a temperature loop. We'll get back to that. So there's several issues here when it comes to control of distillation. The first thing is the issue of how to pair the levels in the top and the bottom. So in this case, I've chosen to use the distillate flow for the level in the top, but I could have used the reflux. That's also fairly common. And the same in the bottom. Here I'm using the bottom flow to control this level. I could have used the heat input. And it's also possible to use the ratios. And all these different choices gives you what we call different configurations. That's based on what. So if you have the LB configuration, it means that after you close the loops for level and pressure, L and V are remaining as degrees of freedom for steady state composition control. So that's the first issue, is how to do the level control and the pressure control. The second issue is then this temperature loop, if we should have it, and where it should be located. Here it's located in the bottom, but it could also be in the top, that we could have a cascade going to the reflux. And finally, there's the composition control problem. Should we control 2 compositions, 1 composition, or maybe no compositions? It actually varies. So let's talk a bit about these problems. Let's start with the temperature control problem. I mentioned that you can view this column almost like a tank with a heavy component goes out in the bottom and the light in the top. This is showing you a composition profile through the system. So see that all the heavy is in the bottom and the light is in the top. And you can view the temperature control as trying to essentially to control this kind of a level between heavy and light, and avoid that we get a breakthrough of heavy in the top or a breakthrough of light in the bottom. And this is a very short integrating process. And to locate the temperature sensor, it should of course be fairly close to the end, but not at the end, because here it's not sensitive. So it should be located at a sensitive location with a high gain. And typically it will be at the middle of the top section or in the middle of the bottom section, maybe a bit closer to the bottom. So people often do is that they look at the temperature profile. So this is the stage here, the temperature here, and they look for places where the temperature drops a lot between stages. And that's actually a good way of choosing locations. Here I've plotted, the blue line is showing you this delta T from stage to stage, and the red line is actually showing you the gain from, if I change the reflux in top to the temperatures, which is the most correct things to look at. And you see there's a good correlation between the temperature profile and the gain. But you need to be a bit careful, because this is for a binary separation, so separating only 2 components. If you have many components, then this is not so easy. Here is a typical temperature profile for a multi-component mixture. And it seems like there's, for example, this stage is very good to use for temperature control. But if you look at the gain, it doesn't correlate so nicely in this case. So for multi-component mixtures, you cannot just look at the temperature profile if you want to select where to control the temperature. Then you need to use maybe some simulation, for example, or you can do an experiment. So in the experiment, you increase the reflux and you look at where the temperature changed the most. So it's quite easy experiment to do. You increase the reflux to the column, look at the temperature, and then you select a place where the temperature changes a lot. And that's going to be following the blue line and not the red line. No, it's going to be it's going to follow the red line and not the blue line. Yeah, and also for multi-component, the temperature will change a lot towards the end, but you cannot use this for control. this change. It will not be. Some people do that, but it's not a good idea for multi-component. So that was about this temperature loop. Then about what I call configuration, which is about the pairing for the level loops. So if you look in the top, the main issue is should I use the reflux or the distillate to control the level? Okay, so this is the top of the column. We have the condenser is here, so liquid comes into this tank, and some of it is sent back as reflux, and some of it is taken out as a distillate product. So normally I would like to use the distillate flow to control level, because I know that the reflux has a much more direct effect on composition, so this is much more effective for composition control. If I use this for composition control, it will be much more indirect. So this is what I would like to do, but I can see some problem here for control, because if this reflux is really large, so as shown here, compared to the distillate, then of course, if I want to make, for example, a change in reflux to control composition, so I increase this one, then this one needs to go down by about the same amount. And if this is small, it might easily become 0, or and then it's not possible to control level anymore. So this doesn't look so promising for a column with a high. So difficult separations have a high ratio L over D, and it seems like this is not going to be working well for difficult separations, like the propylene column. But fortunately, there's one very nice thing here. The first thing is that the tight level control is not important in itself. We can let this level drift a bit up and down. And the second important thing is that if you have a fast inner temperature control, or actually composition control loop, this will provide indirect level control. And that's because the reason for having changes in the vapor flow here or something, or having upsets, is because of change in the composition. And having this temperature loop will automatically or indirectly provide level control. One way of looking at it is if you just imagine a column that has essentially no distillate product, or extremely small. So you're just building up the product in the top. Some separations are like this. You have a very, very small amount of the light component in the feed. You just build the distillate product up in the condenser. This can be controlled actually without any level control. And by having a temperature loop, this will build up by itself, and it will have indirect level control by the temperature loop. So the conclusion is that this control structure, wherever I use distillate flow for level control, this is what I generally recommend for all columns, even for difficult separations. And this gives you what we call the LV configuration, where L and V are left for composition control. So that's my recommendation for how to do this. So you get this structure here that we looked at already. We have to look more detailed, we have the distillate flow controlling level, the bottom flow controlling the level in the bottom. The cooling is controlling the pressure inside the column. That's essentially the holdup of vapor inside the system. And we have left for composition control the heat input, the vapor flow, and the reflux. So the reason we use this LV configuration is because it's the simplest. The level tunings do not matter for column behavior. So that's very important. So even if I change this level controller, it will not change the composition control. And we can also tune this level control doesn't need to be tightly tuned. So we can get small variations in distillate and bottoms. We usually add a temperature loop using L or V. And especially for difficult separations with large L and V, this is a big advantage, and provides indirect level control, and also it breaks the interactions between the top and the bottom.
Just a quick question, Doctor. For this slide, I saw that you put here to control the temperature is either using V or using L. But my question is, what if we use both? For example, let's say we have the desired temperature to be at the top and we have the desired temperature to be at the bottom. Hence, to meet that particular position, I use both V and L to meet that And if I do that, what will be the impact?
You can certainly do that, yes. That's not a, but the most important is to close one, because just closing one breaks the interaction and stops the integration. But it's certainly possible to control both. So that's I'll show an example of that shortly also. So it's not so critical to control both, but it certainly is done quite frequently.
Okay, noted on that. Thank you.
Yeah. Yeah, so this is just showing you then how you can add composition loops on top of it. So you have the temperature, the past temperature loop, in this case in the bottom, and you have an outer cascade that sets the set point for this temperature, and the top you control the composition directly. So this temperature loop, if you have only one of them, normally it should be in the important end. So that's where you need the tight composition control. But in this case, the bottom is the important. So the bottom product is the most valuable. Now, if it was opposite, that this was most valuable, then I will put the temperature loop to the top. And the temperature sensor should be located at a sensitive stage, as I mentioned already. So this is a typical configuration that's used a lot. Although there might be other options, as you just mentioned. Now, I want to talk a bit about what control of distillation, how it should look like. A lot of people think, that distillation is very slow processes, so you need to have slow control. It's not true. You can have fast control of distillation columns, especially if you cannot. That's one of the main reasons for using temperature control, is because if you use compositions, it's often slow because of the delay in the measurement. But with the composition temperature loop, you can have much faster control because temperatures are easy to measure and fast measurements. I want to get rid of this myth of slow control. So to do that, I will compare what I call a perfect operator with automatic control for a typical column. So this column has 40 stages, 99% purity in both ends, relative volatility 1.5, and L over D 5.4. So first I will consider 1-point control, where we control top composition only, and then I will look at 2-point control, where I control both compositions. So this is the 1-point control case. So what we have here is I'm only controlling the composition in the top, and I'm using the reflux to control composition, and the heat input, maybe this is at the maximum or something, so it cannot be used for control. But let's say there's a disturbance here. So this heat input increases. And then you want to keep this composition constant. So first we have the perfect operator. He will step the reflux directly, so shown by the solid line here, to the right new steady state value. And then we'll look at the PI control, where you will have a PI controller to control composition. And it will change the reflux in a slightly different way. It has a slight overshoot here, but looks otherwise quite similar. So the question is, how much difference does this make if I use the feedback control or the perfect operator in terms of the composition response? And I think the result is very surprising and interesting. So the solid line with the perfect operator shows that you have this very, very slow response taking many hours. This is 5-6 hours time constant here. While if you do just a simple PI controller, this is a PI controller with an integral time of 3.6 minutes, then you get much faster response. It settles in a matter of 20 minutes. So this is the top composition, it's constant, and you see there's a change in the bottom composition because that's not being controlled. But you see that in this case that you can make very fast control using, so it seems like it's going to be, you would think maybe the operator would be faster, but the feedback from the temperature actually changes the dynamics of the system, and you get a much faster response. And just to show the 2-point control, which is a bit similar to what you just asked the question about. So here I'm going to want to control both compositions. So I'm going to use the top composition controlled by the reflux and the bottom composition controlled by the heat input. Here I'm using a composition control, but it could be temperature loops. It wouldn't look very different. So again, I'm going to compare the perfect operator that steps L and B directly with the feedback controller. And the objective in this case is I want to increase the composition in the top. So I want to make set point change in the top, and I want to keep this composition in the bottom constant. And so two ways of doing it. One is the perfect operator who knows exactly what to do, doesn't make a steady state change. And the other thing is two PI controllers that control composition. And you see again that there's very small difference between the perfect operator and the feedback control. Seems like, if anything, the feedback control is going to be slower. You see how it's much more slower to make the change. So you would expect that the feedback control would be slower than the perfect operator. But if you look at the results, you see this is not true. Again, it's very slow response with the perfect operator. It's very, very slow to settle to the new steady state. Very, very slow. While the PI controller is much, much faster. There's some interaction to begin with, because interactive, but it's in a matter of 20 minutes, it's settled to the new steady state. So I hope you can then believe me when I say that you should not believe when people say you cannot control distillation columns because they're so slow. It's not true. The key thing is to make at least one loop fast to break the interactions and to get and change the integration, and you can get fast control even for a large distillation column. So conclusion, the experienced operator thinks that fast control is impossible, but with feedback control, the response can be fast. The feedback changes the dynamics and requires continuous active control. And most columns have a single slow mode, so it's sufficient to close a single loop to change the dynamics of the entire column, but it is of course also possible to have several loops changed, or two loops. I'm looking at time. I think I need to just have only 1 point left, which is a bit on advanced control now. I'm not going to talk a lot about advanced control. So advanced control really for me is, in this case, is doing changes to the system. So if you originally have, for example, a composition control, but then you realize you had problems with the maximum capacity, then how to do the switching. And here I'm just showing you how this can be done using simple like maximum switches, or this in a min selector. So for example, if I have the composition control running normally, this is the important end. I have a temperature loop here. Everything is running great. But then I reach the maximum pressure drop in the column. Then what you do is you have this controller running in parallel. And when it reaches the maximum pressure drop, you have a min selector, and this DP controller will take over. So that's one way of doing changes. And you may also add the feed forward control from the feed rates. In this case, typically to the bottom. But the top is already well controlled using the temperature loop. So you can have a feed forward from the feed rate to the bottom to make it respond more quickly to feed changes. So there's lots of things you can do to improve control and distillation. But normally, as I said, I recommend the basic LV structure for most cases. In terms of another advanced control scheme, this is showing you a case where the bottom product is the valuable product. And so normally I'm controlling the bottom purity using the boil up. But what could happen is that the boil up reaches its maximum. So then, of course, you cannot use the boil up anymore. So then I would like to take the reflux take over. So we have this split range control, let the reflux take over with the min selector here. But then what might happen again is that when you're using the reflux, you lose control of the top composition, and the top composition might reach its limit, its specification. Then you need to cut back on the feed. So when this takes over, then you will start cutting back on the feed using this loop here, and this way you can control. You can change the control in a quite simple way. Now, in this case, you could use MPC. MPC would maybe be a simpler solution for this kind of problem. The problem with MPC, of course, that it requires more effort in terms of making models and implementation. But you could easily have used MPC for this particular problem and made it work. But I just want to tell you that if you're systematic with what I call advanced control, which is something I worked on recently, this is a quite recent publication from 2020, you can actually do essentially the same thing with these structures as you can do with MPC. So it's really a matter of choice of what you prefer. But if there's very interactive systems and you want, especially maybe for some feed-forward things, MPC is definitely a good option. So finally, conclusion on distillation control here. I would say it's not as difficult as people often think. I recommend the LV configuration for most columns. Use log transformation to reduce nonlinearity. Something I didn't talk about was composition estimators, shock sensors. Usually for the composition control, you often have estimators based on temperature to make sure that you don't need to have so much delay. So you usually use composition estimators based on temperature as soft sensors. You usually use a temperature loop, at least for difficult separations, and proportional control is good enough usually for this loop. And you may use model predictive control if strong interactions between the loops, but otherwise classical advanced control structures also can take care of changes in active constraints and so on. And this is the conclusion for everything. I don't think I'll go through everything here. I think this can be a good point for making questions, because here I have summarized the main things. I talked about distillation as a separation process. It's quite efficient. I talked about modeling. It's fairly simple in principle. I talked about dynamics. There's one slow mode. I talked about operation. Often it's to control both compositions, but not always. And I talked about control, which involves stabilizing the column, and then involves controlling the active constraints. I said that you can use usually quite simple PID controllers, but also this is a good process for using MPC. I didn't talk about MPC today, but many vendors do provide MPC solutions. So, but of course, they still have to follow the same recommendations as I have in this talk. So thank you very much so far for listening to me. I'm very happy to answer questions or comments that you might have.
Thank you very much, Professor Scott J. for the mind-opening presentation, especially in this area of distillation column control. Now I'm open for questions for everyone. If you have a question, you can just ask the question. Just unmute your mic. Agus, do you have questions, Agus?
Yes. Maybe can start with me. Prof. Scott Jusat, I think you are on point when you are saying that distillation control is simple if we can maybe break the delay in one of the control loop. Do you think the inferential system? I mean, just now you mentioned about concentration estimation using the tray temperature. Do you think those inferential system can further fasten the loop?
No, not really by themselves. They usually we use this because of the delays in its composition measurements. So we need the inferential systems, yes, because we need usually to control compositions. So they're an important part of the system. They're not really, I won't say they're further improving really. Well, like in some cases they can replace the temperature loop, of course, because they also will be quite fast. So it's something you should, for most columns, they need to have estimators, it's very common to have. I didn't talk about it today, but it's an important part of the system.
Okay, sure.
Okay, there is one question here from a participant in the chat. The first question is, how can control helps in separation process with low relative volatility, which is the difficult separation type of column?
Yeah. So low relative volatility are the most difficult for control. And it has this strong interactions, for example, and has slow dynamics. So especially for those separations, I think it's important to have at least one loop being tightly controlled. It doesn't need to be temperature. It could be composition. It could be some estimator. But because you need to have this loop to break the interactions and to stop the integration. But I think if you do that, you will find that even very difficult separations can be well controlled.
Okay. There is another second question. What robustness in distillation column control?
Yes, robustness. That's was my topic for my PhD. So if you don't, if you're not able to break the interactions, and you have both loops being fairly slow, it's a very interactive system, very difficult to control. Then robustness is going to be bad. But as soon as you try to control at least one temperature tightly, then some of the robustness issues goes away because it becomes less interactive. So I don't know what the question is about, if it's about robust control, or what's the main thing they're asking about. But in terms of robust control, I would say that the thing that saves you really is that you have this liquid flow dynamics. It took me some time to realize it when I was for my PhD, that this liquid dynamics were helping you a lot for control. You know, the fact that it takes time for liquid to go to the bottom, and this is really helpful. And we need to make use of it in the control.
Okay. Okay, we have.
Okay. Then.
All right. Okay, you go. You go first. All right, continue with the
Hello.
question. Yeah.
Yeah. Come on in. Can I ask question?
Yeah, you can ask question. Don't worry.
Okay. No. Okay. Prof. Sigurd, yeah, very nice to have you here. Aslan Hussein from Museum Malaya. Far, near but far. So far, but we are near on the online. Yeah. Thank you very much for your interesting talk and a very interesting part. Basically, I think you have broken two myths in your talk, two myths. The one that you talk about slow control, which is quite clear, it's not true. The other myth is about that many people think that actually there's not much left for research on control, which actually you have shown us there actually is still a lot of things to be done for research in control. So other than what you are doing, can you give us some other things that maybe the researchers can look up into? I mean, trying to do the latest part, research on distillation column. I'm talking more about distillation column. I mean, what are the other things maybe people can still look into, still try to solve using conventional or advanced control? As I said, you have one example or two examples. Is there any others that you can give us an example of? Yeah.
Well, there's many cases. This for control, distillation usually is part of a big system. So in terms of the whole integration and the recycle around the system, I mean, it's distillation itself is actually a difficult process from a control point of view. It's a good process to learn control, I would say. For teaching, it's good. And there's many different distillation columns. There's many different cases. You know, if you look at the real applications, you will see that what the control objective is changes a lot from case to case. And also, you have more complex separations. You know, you have columns with side streams. You have columns. You have isotropic separations, which are difficult. You have Also, this I didn't talk about today, but you have this integrated column sequences, like the divided wall columns. I mean, there are many things in distillation that still is people haven't really come up with good schemes on how to control them in general. I presented only today the simplest case of one single column. I looked a bit into how in some cases that you might need to cut back on the feed, and how to do changes. In terms of research, you can say that control has it has a lot of theory already done, and that's so. I don't think the distillation is anything special here. I think distillation is a very important process, and it's very interesting for control. It's one of the best processes to study for control, for sure. If you want to look for an interesting process and study control, distillation is probably the best, I would say.
So there's still many topics really to look into in research. It's not just it's not the end. There's a lot of things.
I think so. Yes, and each column is different. It's
yes.
a lot of diversity in columns. There's a lot of diversity, and so the solution I present today was to try to give like one thing that works in most cases, but and just show you. I think it was clear from what I presented today. There's a lot of interesting things on distillation, which is important. And it's it is a very interesting process.
Okay. Thank you for enlightening us on this issue. Thank you very much.
All right, thank you very much, Prof. Azlan, for the questions. We take question from chat. In case we apply pinch analysis and heat integration on distillation column sequence, would that affect the control system and also the control law that we are using?
Yes, that's a good question. Of course, if you have a lot of integration that you get from pinch, it can have a large effect. Because it means that the column will be very coupled to other units. This can make it very challenging, obviously. So usually what you try to do is do it unit by unit and try to get reasonably tight control of the column, and then you have on the slower time scale you do the integration. But sometimes integration is very tight and it can make it very difficult and challenging. So there was asked a question about challenges for distillation control. I would say that this is one of them, definitely. So it's not like it cannot be done. It's not impossible to do the control, but it gets challenging, and you might need to change the control strategy that you're using. So yes, so the question. It's a good question, and the answer is yes. This can have a large effect on the control. It can change things what I told you about. Yes.
Yeah, I also agree with your answer, because when we do the heat integration, some of the degree of freedom will lose over there.
Exactly.
We lost some of control degree of freedom, especially from the condenser and also from the reboiler.
Yes, that's true. But you still need to do to try to do overall objective is to stabilize and do optimal operation. But generally, you always find that you can do it, but it's just going to be more complicated, or you have to do some more thinking and how to do the control. It makes it again very interesting process. Of course, it's. I'm not saying it's simple, but it can be done, I would say.
Yeah, I also agree with you. Okay. We'll check one question again from the chat. Is it necessary to control the top temperature, even if our desired product is at the bottom?
Well, as I said, if the most important product is in the bottom, then you would. It's not a good idea usually, because that's a fast loop, the temperature. So usually you put the temperature loop in the end where you have the important product. There might be, of course, there are cases where this doesn't apply. Maybe the cases where the temperature profile is very flat, all kind of things. So there can be exceptions. But if you try to control, the bottom is the most important, and you have a temperature loop in the top, it will tend to be strong interactions. Maybe this is the case where you need to think about using MPC or something. I didn't talk about MPC because I want to show that in most cases you can do okay with conventional control. But if you get to very interactive processes, it can be very helpful to look at MPC solutions. And for MPC solutions, you usually put them on top of some base control, but it's also possible to have them almost running at the on the individual even level loops. But normally it's put on top of some base control, which includes level control and maybe a temperature loop.
Okay, this is question from me. So during your presentation, I really interested with this statement. You have stated there most of the distillation control papers are not study about distillation. Okay, rather my control strategy is this. So I do also with your statement. Okay, so most of the distillation column control papers, they're not study about the control about the distillation dynamic. Basically affected by the design of the column itself. So in this case, do you agree with my statement that the dynamic, the control problem of this distillation comes from the distillation dynamic, and this dynamic comes from the problem in the design of the distillation column? Can you comment on that with my statement?
Well, I'm agreeing with what you said, that in many distillation papers, they don't really talk about the distillation. They talk mostly about their control theory. And the model they use is often too simplified. I think that's what you're talking about. And if you use the wrong and simplified model, of course, you will not get good conclusions. So in many cases, or at least some cases, for example, people don't even include the liquid flow dynamics, and then they will reach wrong conclusions on distillation control. Also, they assume that you can have perfect measurements without noise in the column ends, which is very unrealistic. The reason we don't control the temperature in the end of the column at the top is because it's very sensitive to noise. That's why we need to move it into a more sensitive location. If we, for example, neglect completely noise on the measurement, then you can make very unrealistic designs. Especially if you look at electrical engineering papers, or people who, especially like old papers on distillation from many years ago, but people were just using state space models, you can get very unrealistic conclusions about control, for sure.
Okay, there's more questions here from the chat. Okay, let's take this question number 5. Knowing that a robust control method tends to be conservative, so what kind of robust control technique would be appropriate for the distillation column control?
Well, I have. In this talk, didn't talk so much about robust control. I talked about just using simple PID control loops. They are usually robust in themselves. To get problems with robust controls, usually when you have a lot of interactions, and I was saying, people, robust control is not used a lot in practice for distillation today. I would say, because one reason is it's not such a difficult problem as I thought originally, because of this decoupling with the temperature, or with this liquid flow dynamics. So it's not a very difficult problem for robust control, I would say. Robust control methods come in when you have strong multivariable problems, and the MPC, for example, is not good, not robust. Then you can go to robust control. I wouldn't say that distillation necessarily is such a case. There could be cases, but especially if you have maybe more interactions and more heat integration. It could be more need for robust control methods, but I haven't really looked at that.
Okay. Another question from Chet. For high nonlinearity situation in the distillation columns, would data-driven, as known as machine learning-based control, would be preferable to classical control theories?
Well, I've mentioned already that some tricks you can use from nonlinearity, taking the log of the composition and so on. Now, in terms of machine learning and things like this, difficult to say. Distillation columns are fairly easy to model, so it makes them good candidates for some model-based control. Machine learning is more data-based, of course, and especially for processes where you don't have good models. This is something that seems like a good solution. I'm looking into database models, and machine learning things, also for distillation. So it certainly has a role, but I think in most problems can be solved using what we have today. Things I explained today. But there are definitely exceptions. I don't really have a good answer to this.
Okay, thank you, Prof. Is there any question from the audience?
I saw someone was asking someone.
Okay, there is the last one here from Dr. Aslinda. What would be the direction of distillation column control in the future?
That's a tough question.
Very tough question.
I think we mentioned already lots of these things about more integrated processes, and also both you have these direct coupling things. You have also separations involving isotopes, more complex mixtures. There's a long list of things to look at. Now, in terms of fundamental things, and it's a complicated process, interesting process. There's lots of things to do. I don't know if I can point out any one single thing to do. What I can say is that I think that these processes can be controlled, and we should not stop working on them, because they are important processes, and the control can be improved. And there's still a lot to do, at least in practice. If you look at how real columns are operated, it's often not operated well. Actually, I'll tell you, the main problem when I go in practice and I see a column that's not operated well is usually because of the level control. The level control usually often is the main problem, because people use too much integral action and then start oscillating the levels. This is just a warning to people in industry. If you have problems with oscillating columns, try to look for the levels first and make sure this is not the reason. But anyway, in terms of future research, it will remain an important process, distillation. For many different separations, it's used a lot, and it remains a difficult problem to control. I would say it's interactive. It requires people that understand the process. It's not something that's so easily controlled by anyone. So I think it's important to keep research going, just because it's of the importance of the process itself, which will remain there.
Okay. Thank you, Prof. Is there any other question?
Dr. Kama, there is one question goes to me privately. Let me try to read.
Okay.
Yeah.
Continue. Yes, please.
Yeah. So, have you ever implemented a flooded drum pressure control? Literature review indicate that this scheme is sometimes used when all the overhead vapor is condensed.
Yeah, I didn't talk about this control of condenser level and so on. I haven't looked at it a lot myself. I've read the literature, like what Leuben writes and so on. I think the solution, it of course varies, depending on each case. There can be special things. And so I'm sure what you say can be used in some cases. It's something that I haven't really looked at a lot myself, but it just shows you the diversity of distillation. There's so many things you can look at, there's so many things I didn't talk about today. That I was just trying to talk about the main things. I did some work on this some years ago, but I don't quite remember what I was doing, so I can't really respond to it.
Okay. So I guess, is there any question from your friends?
Let me try to screen through once more time. Yeah.
So while,
Yeah.
Prof. Scottis, I just want to comment on your conclusion number 5 on the control. Okay, the first point there, first stabilize the column, which is you can stabilize using level, pressure, at one temperature. So I do agree with this. So I have a lot of analysis on the advanced process control for a single distillation column. So if I look, the one that which is basically for, in my opinion, the practical strategy, they always maintain the level at the reflux drum and also at the bottom as a feedback controller. They don't change it. They don't do some cascade on it. The same thing also with the pressure. And the only thing that they change it, they make advanced is just for the other two degree of freedom, which is top and bottom composition. So yeah, I do believe that this is also relates with the third law of process control, always control level. So why we need to control level? Because we're able to stabilize, okay, stabilize the mass balance, stabilize the column easily. Once the level is maintained, then the column will be stabilized because the mass balance is already stable there. All right, that's why I really agree with your first point there. Make sure that stabilize the column first. You can apply whatever advanced strategy that you want. Stabilize the column first.
Yeah, I agree. And in terms of level control, what you can see, if you can have cases, for example, where the feed rate or the distillate flow could be given, then you might need to control the bottom level using the feed rate, for example. But that's more in a plant-based session. This is something I work quite a bit on. If you look at the column as part of a big system, in some case the bottleneck could be after the column, it could be before. And then you might need to rearrange the levels, but that's the only case is when it's when somehow the feed, for example, the column is no longer suddenly a degree of freedom. Then you need to use the feed to control the level typically, or might need to do, or at least do some rearranging of the system.
Azran, do you want to ask another question, Prof. Azran?
Yeah. Sorry, Prof. Sigurd, just maybe an opinion from you on teaching of process control. What do you think we should be adding now in our control syllabus? The standard ones, we're using all the standard Leuben and Malichem and all those things. But is there anything that is missing now that we should be teaching the students for process control? Maybe distillation, maybe anything. Can you give us some things that maybe we're missing?
Is it for undergraduate?
Yeah, for undergraduate. Yeah, mainly for undergraduate. Yeah.
What I'm teaching now, is with something that's not taught a lot. Is I'm teaching them how to do changes in constraints. I'm teaching about split range control. Or here, if you want to use split range control, you can either use split range control. You can use here you could have used 3 control with 3 different set points, slightly different set points. or you could use also some valve position control to do this. So I try to teach them some of these things. I try to teach them something about min selectors to do changes in CB switching. Some of these things that people have used in industry for 50 years, but no one is really teaching to the students. I mean, it's okay to teach them MPC, but they should also know this more, how can use this more standard scheme. So I'm one of the few people, actually, I'm teaching this to my students, what I call advanced, classical advanced control schemes, which people usually are left to learn by themselves when they get out to industry. So I try to give them some basics on how to do this. I also teach them PID control because they need to know how to tune the PID control loop when they get out. And in terms of distillation, it's a good process, but of course it's a bit complicated, you can say. So, you know, it's, I mean, that's one of the you know, how much time can you spend on one process? That's a bit the question. Now, distillation is important, but there's also a lot of other important processes. So I do mention distillation as an example. So I do some teaching on distillation for my undergraduate students. Yes.
How many classes do you have? Do you have only one process control class for the chemical engineering? Or?
No, we have one. No, we have two, you can say, but most of them only take the one.
Yes. Okay.
And we have some advanced control, and the advanced control we do more on this thing, and we have a module on MPC. We have two modules for the advanced control. One using MPC and one using standard this thing. Okay. We want to teach them both. I shouldn't only know one, because, you know, when they get in industry, they sometimes you use MPC, sometimes you use more classical control. You should know both of them.
Exactly. Okay, thank you very much for your answer.
Okay, thank you, Prof. Azlan, for your question, and also thank you, Prof. Khojisat, for the response. Dr. Agus, is there any other question from the chat?
No questions in the chat box. Yeah. On behalf of the society, thank you very much for today.
Thank you for inviting me.
Yeah, and we hope to have you in the near future.
Yes, I hope to see you in real life in the near future. Maybe I can see in Malaysia or here in Norway.
Yeah. Sure. Yeah.
Thanks a lot for listening.
Yeah, thank you very much, Prof.